Welcome. This tutorial discusses the concepts of sampling and sampling distributions. If you recall from the Introduction to Statistics tutorial, a sample provides us with a glimpse of what the bigger population looks like. When we sample, we examine a few elements from a population, and based on our results, we get an estimate of the population mean or an estimate of the population proportion. So instead of examining an entire population of, say, 20,000 factory parts, we take a subset from the population, say a sample of 200, and then use those results to infer something about what the population looks like. Let's say we take a sample of 200 cereal boxes and weigh the contents to get a sample average weight, X bar, of 15.8 ounces. Does that mean that the true population average mu is also 15.8? If we could weigh all the cereal boxes we produce, would we get a population mean that is exactly the same as a sample mean? The answer is probably not. Since the estimate of the population mean is coming from a sample, we can expect some estimation error. The question is how large that error might be. The same can be said about the sample proportion and its usefulness in estimating the true population proportion. If we have 20,000 factory parts and we sample 200 of the parts to find that 5 are defective, then the sample proportion of defective parts is 5 divided by 200, or 0.025. Does that mean that the true population proportion of defective parts is also 0.025? Does that mean we would expect to find 20,000 times 0.025, or exactly 500 defective parts from the entire population of parts? The answer is no, of course not. It might happen, but we would expect some error. We might find 498 defective parts or 502 defective parts, but we would expect the population proportion to be 0.025 plus or minus some error. When we take a census, that is, we examine every element in a population, we get what is called a population parameter. For the true population mean, we use the symbol mu. For the true population variance, we use sigma squared. And for the true population proportion, we use capital P. Some statisticians use the Greek letter pi. When we take a sample, we get what is called a sample statistic. In this case, we don't have the true population mean. Instead, we have a sample mean, and we call it X bar. We also get a sample variance, which we call S squared, and for the sample proportion, we use P bar. Here is a table comparing some more symbols we use depending on if we are looking at population parameters or sample statistics. We just reviewed the mean, variance, and proportion for both populations and samples. I added here two more symbols. We use big N for population size and little n for sample size. In sampling, we take what is called a probability sample or a non-probability sample from the population. Researchers like probability samples because it allows the statistician to make statistical inferences about a population that are more sound or more valid than the inferences obtained from non-probability sampling methods. We will discuss some of the various types of probability and non-probability methods that are used at the end of this tutorial. But for now, it is important to understand that with probability sampling, each item in the population has a known non-zero probability of being selected. Whereas with a non-probability sample, the probability of selecting an item is unknown. The most typical probability sample, and the simplest to use, is called a simple random sample. The definition of a simple random sample is when a sample size of little n is taken from a population of big N such that each possible sample size of little n has the same probability of being selected. To do this, each item of a population is assigned a unique number, and then a random number is generated either using a computer or a table of random numbers to decide which element will be selected. In this manner, every element in the population has an equal chance of being selected. The most typical type of non-probability sample you are probably aware of is a convenience sample, where the researcher samples the items that are conveniently available. The sampling methods we just discussed are referring to sampling from finite populations. What about sampling from infinite populations? An infinite population can be referring to a very, very large population of which we really don't know the number, or an ongoing process such as manufacturing, where the process goes on as long as the machines are running. Since in both of these cases there is no real upper limit for the numbers, we can't generate a list of all the elements from which to choose our sample. In the case of an infinite population where we don't have a frame to pick from, we must make sure to pick a random sample so that two criteria are fulfilled. 1, each element must come from the same population, and 2, each element must be selected independently. So for our example, let's say we manufacture light bulbs. The process is ongoing, so the number of light bulbs produced is theoretically infinite. To take a random sample of, say, 50 light bulbs, we would need to first ensure that each element comes from the same population. We do this by making sure the light bulbs come from the same plant and at approximately the same time every day. The plant may have day workers and evening workers, so we must make sure that when we are sampling the light bulbs, they come from the same shift of workers and at the same time of day. The second criteria is that each element is selected independently, so that choosing the first light bulb doesn't in any way affect the second light bulb. We have to wait until the light bulb is produced and off the line to take it and use it as a sample. If we take it from the line just after it is made, this might cause a gap in the assembly line and affect the subsequent light bulbs that are produced. We have to study the process to ensure that by taking the light bulb, we don't affect the production of future light bulbs. That would fulfill the second criteria of independence. Let's look at another example of sampling from an infinite population. Let's say we are sampling fans attending a sporting event. The first criteria is that the elements are from the same population. If we are interested in the paying customers, then we need to make sure that is who we are sampling. If a worker is also viewing the event but works at the stadium, he would be from a different population and we would not interview him. First, we would have to define the population, say all paying sports fans above the age of 18. And then we make sure that each element selected is part of that population. The next criteria is equally important. The elements must be independent from each other. If the interviewer has control over who he picks to include in the sample, he may only pick fans sitting in a certain section of the stadium for convenience sake. These seats might be the most expensive or the cheapest, making those fans economically different from the rest of the fans in the stadium. Fans sitting in a group may be like-minded people, and interviewing them might again result in a biased or skewed sample. In both these cases, the interviewer would get a biased sample. We have a name for this type of a bias. It is called selection bias. That is why the second criteria, that each element must be selected independently, is so important. In sampling, it is important to have a representative sample. That means that the sample is a good picture of what the population looks like, since we will be using the sample statistics to infer something about the population. We want the sample to be a miniature picture of the population, so we want the sample to be as unbiased as possible. That is why a random sample is so important. Now let's talk a little more about why we take a sample and what we can use it for. Remember, the reason we take a sample is to get an idea about the true population parameter. If we could take a census, we would, but normally we don't have the time or money to interview an entire stadium full of people, so we take a subset of the population and call it a sample. In the case of manufacturing light bulbs, we can't sample every light bulb we manufacture, especially if the sampling process destroys the light bulb, as would be the case if we want to measure the average amount of time a bulb burns. So we would need to take a sample and use the measurements we get to infer something about the population. Measurements we take from a sample are called statistics, or sample statistics. Measurements from a population are called population parameters. Sample statistics are used to infer the values of population parameters. These inferred values are called point estimates. The following sample statistics are used as point estimators for their corresponding population parameters. X bar is the sample mean and is used as a point estimator for mu, the population mean. S squared is the sample variance and it is used as a point estimator for the population variance. S is the sample standard deviation, and it is the point estimator for sigma, the population standard deviation. And P bar is the sample proportion, and it is used as a point estimator for P, the population proportion. The numerical value we get for any of these sample statistics, X bars, S squared, S, or P bar, is called a point estimate. It is important to understand that these sample statistics are estimates of the true population parameters. We don't know what the true population parameter is, so we use the sample statistic to estimate it. So for example, let's say we take a sample of 50 light bulbs, and the sample mean of how many hours they burn is an X bar of 1045 hours. It might be that if we could actually measure every single light bulb, the bulb's true average mu is 1050 hours. But we would never know that. We can only go by what the sample tells us. Let's say we sample 100 stadium fans and ask them how many bought at least one hot dog at the stadium. If 62 of the fans say that they bought at least one hot dog, then P bar is 62 divided by 100, or 0.62. Does that mean that the true population parameter P is also 0.62? It might be. It also might be 0.65 or 0.55 or any other number. If we take a random sample that is unbiased, then we can assume the sample statistic gives us a good estimate of what the population parameter is. Now let's say we take another sample of 100 stadium fans, and this time 59 fans say they bought a hot dog. Now the sample proportion is 0.59. In fact, every time we take a sample of n equal 100, we can expect to get a slightly different sample proportion as a result. The same is true for our light bulb example. In the first example, we said that a sample of n equal 50 light bulbs produced a sample mean of 1045 hours. Now let's take another sample of 50 light bulbs and measure how long they burn. Do you expect that the sample mean from the new sample will also be exactly 1045 hours? Do you expect every potential sample of 50 light bulbs to give a sample mean of 1045 hours? This could only happen if there is no variation in the data, that each light bulb is exactly the same. But they aren't. Some light bulbs will burn a little longer and some a little shorter, but in the first example, they burned an average of 1045 hours. The second sample will probably produce a different X bar, maybe 1052 hours. A third sample might produce a sample mean of 1043 hours. If we keep doing this, taking a sample of 50 bulbs over and over and over again, say 500 times, we will get 500 X bars, or sample means, one for each of the samples we take. Some of those sample means will be on the low side. We might even get an X bar of 950 hours, and some of those sample means might be on the high side, say 1150 hours. But most of those sample means will be in the middle, clustered around the true population mean. Here is what a distribution of all of those sample means might look like. In this table, you can see a theoretical distribution of sample means, X bars, shown as a relative frequency histogram. This is if we take a sample of n equal 50 light bulbs over and over and over again, 500 times, so we have 500 samples of size 50 and 500 sample means. This picture is meant to show the distribution of those 500 possible sample means. We could extend this example to a scenario where we take not just 500 samples of 50, but all possible samples of size 50. If we were to take sample after sample after sample of all possible samples from a population, then what we have is called a sampling distribution. If this sampling distribution is measuring X bar, the sample mean, then it is called the sampling distribution of X bar. The definition of the sampling distribution of X bar is the probability distribution of all possible values of X bar. Just like with any other distribution, the sampling distribution has its own expected value or mean, and its own standard deviation, and its own shape. To begin with, let's discuss the expected value of X bar, that is the mean of all possible sample means. In the past, we calculated the expected value of X for a single sample. Now we have multiple samples, each with its own X bar, so we are looking to calculate the mean of all of these means, and that is called the expected value of X bar, which is equal to mu. This means that if we use simple random sampling, the expected value or mean of the sampling distribution of x bar is equal to the mean of the population, mu. So if the true population mean for light bulb hours is 1050 hours, then the mean of all possible sample means is also 1050 hours. Each individual x bar may or may not be 1050 hours, but the mean of all the possible means will be equal to 1050 hours, and that is the true mean. Every once in a while, we will get an individual sample mean that is equal to the true population mean. In this case, we might get an x bar that is 1050. When this happens, that point estimate is called an unbiased point estimate. Just as the sampling distribution has its own x bar, it also has its own standard deviation. We will call this the standard deviation of x bar. It is also called the standard error of the mean, and it looks like this: sigma subscript x bar. Remember, sigma without any x bar is the standard deviation for the population, so sigma subscript x bar is the standard deviation for the sampling distribution of x bar. To calculate sigma x bar, we have two formulas, one for finite populations and the other for infinite populations. The formulas are as follows. For a finite population, sigma x bar, the standard error of the mean, is equal to the square root of big N minus little n divided by big N minus 1 times sigma over the square root of little n. For an infinite population, we simply take sigma divided by the square root of little n. Remember, big N is the population size and little n is the sample size. The part of the formula that has the square root of big N minus little n over big N minus 1 for a finite population is the only difference between the two formulas, and this part of the formula is commonly referred to as the finite population correction factor. When the sample size little n is close to the population size big N, this factor calculates as close to 1. Because of this, the difference in the results between the two formulas is negligible. So we use the formula on the right for infinite populations when calculating the standard deviation for x bar. To illustrate how this formula is used, let's take a sample of n equal 50 light bulbs and get a sample mean x bar of 1045 hours. We know the population standard deviation is 65 hours. Then the standard deviation of the sample mean x bar would be 65 divided by the square root of 50, which is 9.19. We could take another sample of n equal 50 light bulbs and get another sample mean and another and another and another. And if we plot all of these sample means into a histogram, we would get something that looks like this, a normal distribution curve. In fact, the larger our sample size is, the closer the sampling distribution will approximate the normal distribution curve. This is called the Central Limit Theorem. It states, when selecting random samples of size n from a population, the sampling distribution of the sample mean, x bar, can be approximated by the normal distribution as the sample size becomes large, no matter what the underlying distribution of the population is. So let's understand what this is saying. The Central Limit Theorem says that even if we have a population with a skewed distribution, or a uniform distribution, or any type of distribution you can think of, as you pick larger and larger sample sizes, the sampling distribution of all the possible x bars will approximate the normal distribution. From a practical perspective, we want to know how large a sample is large enough. After many studies by statistical researchers who have studied the sampling distributions of x bar for many types of populations, they have concluded that a sample size of 30 or more is usually large enough to approximate the normal distribution. If the population is known to be highly skewed or with many outliers, then a sample size of 50 might be more appropriate. In real life, no one goes out and takes every possible sample of n equal 50 to plot the sampling distribution of x bar. You might as well just take a census. So why are we so interested in the distribution of all possible sample means? The reason is that we will be using the value of a sample mean to estimate the true population mean. By understanding the sampling distribution of all possible x bars from a particular sample size, we will understand more about the difference between the value the sample mean gives us and what the true population mean is. Let's try to understand this using an example. Let's say the manufacturer of light bulbs would like to estimate the true population mean of how long his bulbs burn to within 10 hours. Some samples he takes of n equal 50 will provide good estimates of the true population mean mu, and some of the samples will happen to pick extreme values, either too high or too low, and they will give poor estimates of the true population mean. Let's say we know the true population mean is 1,050 hours. What is the probability of taking a sample and obtaining a sample mean between 1,040 hours and 1,060 hours? 1,040 hours is 10 hours below the mean, and 1,060 hours is 10 hours above the mean. And remember, we want the manufacturer to estimate the mean to within 10 hours. This distribution curve illustrates what we are asking. Here you can see the true population mean mu in the middle is 1,050. Then we mark off an area below the mean at 1,040 and above at 1,060. This area is shaded, and we are asking what is the probability that x bar, the sample mean, is between 1,040 and 1,060 when the true population mean is 1,050. Again, in real life, we don't know what the true population mean is, but to understand how sampling distributions help us, we need to assume that we have this knowledge, that we know that the true population mean is 1,050. So going back to this distribution, you can see the shaded area under the curve is the probability of obtaining a sample with a sample mean of between 1,040 and 1,060 hours when the true mean is 1,050. Now, in order to find this area under the curve, we have to convert the x values to standardized z values. We learned how to do this in an earlier tutorial. Please review that if you don't remember how to use a z-table. The formula we use to standardize x values to z values is x minus mu divided by sigma. For a sampling distribution, we have to adjust the formula x minus mu divided by sigma subscript x bar. Now remember, sigma x bar is also called the standard error of the mean, or the standard deviation of the x bars, and it is calculated by dividing sigma by the square root of n. So now the formula reads x bar minus mu divided by sigma over the square root of n. So substituting an x bar of 1,040, we get 1,040 minus the theoretical or hypothesized value of the population mean 1,050 divided by 65 over the square root of n. This is negative 10 over 9.19 for the sample size of 50, so we get a z-score of negative 1.09. This we can mark on the lower end of the distribution for the x value of 1,040. Now when we calculate the z-score for an x value of 1,060, we get 1,060 minus 1,050 over 9.19, or positive 1.09. And we can mark that off as well. What remains now is to look up this area in the z-table to determine the area under the curve between a z value of negative 1.09 and positive 1.09, which translates into x values of between 1,040 hours and 1,060 hours. Looking this up in the z-table, we first look up the cumulative probability of x less than z, or less than 1.09, so we look up 1.0 on the left side of the table and 0.09 at the top, and we get 0.8621. Then using the negative table, we look up the area below negative 1.09, and we get 0.1379. Now subtracting 0.1379 from 0.8621, we get the area between negative 1.09 and 1.09, and that is 0.7242. This shows us that a simple random sample of 50 light bulbs has a 0.7242 probability of giving us a sample mean that is between 1,040 hours and 1,060 hours. That is, there is a 0.7242 chance that the sample mean will be within 10 hours of the true population mean. This difference between the sample mean and the true mean is called sampling error. Therefore, there is 1 minus 0.7242, or 0.2758 probability that the sampling error will be more than 10 hours. We can reduce the sampling error by using a bigger sample size n, or we can be satisfied with this amount of sampling error. Why would increasing the sample size reduce our sampling error? Remember, the standard deviation of the x bars, also called the standard error of the mean, is sigma divided by the square root of n. For our example, we divided 65 by the square root of 50 and got 9.19. Now let's say we increase the sample size to 100. What would happen to the value of the standard deviation for the mean? Would it become larger or smaller? If we increase the sample size, we are automatically reducing the amount of sampling error we will have, so the standard error for the mean should be smaller. Let's see if this is true. 65 divided by the square root of 100 is 6.5. So now our standard error is only 6.5, whereas before it was 9.19. We see how the sample size has an inverse relationship with the standard error. By increasing the sample size, we have decreased the standard error or standard deviation of the mean. This means that the larger the sample size, the higher the probability is that the sample mean will fall within the specified interval around the mean. Take a look at these two normal distribution curves and see how they differ depending on the sample size. The shorter, fatter curve has a smaller sample size of n equal 50 and a larger standard error or standard deviation of 9.19, so the distribution of the sample means is greater for n equal 50. The taller or skinnier curve is from the same population, but here we increase the sample size to n equal 100, so the standard deviation of the mean is only 6.5, resulting in less dispersion. Just as we have used x bar to estimate the true population mean, we can use p bar as a point estimator for the true population proportion. The formula for computing the sample proportion is p bar is equal to x over n, where x is the number of elements in a sample that possess the characteristic of interest, and n is the sample size. The sampling distribution of p bar is the probability distribution of all possible values of the sample proportion p bar. Just as we discussed the sampling distribution of x bar, p bar follows the same logic. To calculate the expected value of p bar, we use the following formula. The expected value of p bar, E of p bar, is equal to p. That means that the expected value of p bar is equal to the population proportion p. The standard deviation of p bar is calculated in the same way as the standard deviation for x bar. We are again concerned with whether the sample comes from a finite population or an infinite population. Here is the formula. You can see on the left we have the finite population correction factor of the square root of big N minus little n divided by big N minus 1. As we discussed earlier, when the sample size is large enough, this correction factor will be approximately 1. So we will almost always use the formula on the right for infinite populations. In the case of x bar, we use a rule of thumb that is n should be greater than 30. For proportions, the rule of thumb is that little n divided by big N is less than or equal to 0.05. So let's look at this more closely. The standard deviation of p bar, shown as sigma subscript p bar, is equal to the square root of p times 1 minus p divided by little n. Let's say we know the population proportion of fans who order hot dogs is 0.65. If we are sampling 200 fans from a stadium of 20,000 fans, then little n divided by big N is 200 divided by 20,000, which is 0.01. which is less than or equal to 0.05, so we don't need to use the finite population correction factor. To calculate the standard deviation for p bar, we take the square root of 0.65 times 1 minus 0.65 divided by 200, and we get the square root of 0.65 times 0.35 divided by 200, or 0.0337. It can be shown that the sampling distribution of p can be approximated by a normal distribution whenever the sample size is large enough to satisfy two criteria. One, that n times p is greater than or equal to 5, and two, that n times 1 minus p is also greater than or equal to 5. If these two criteria are satisfied, then the sampling distribution of P can be approximated by the normal distribution. For our hot dog example, n is 200 and p is 0.65, so n times p is 130, which satisfies the first criteria that n times p is greater than or equal to 5. Is the second criteria also satisfied? Let's see if n times 1 minus p is greater than or equal to 5. 200 times 0.35 is equal to 70, so the second criteria is also satisfied. Let's see how this can be applied to our hot dog example to determine the probability of getting a sample P that is within 0.05 of the population proportion of fans buying hot dogs. Since the population proportion is 0.65, that means we want to know what the probability is of obtaining a sample with a sample proportion P between 0.60 and 0.70. This graph shows the area with this probability shaded in. Using the normal distribution to approximate the sampling distribution of p-bar with a population proportion of 0.65 and a standard deviation of 0.0337, we first need to standardize the sample proportion p to a z-score. Now you remember for x values you standardize by using the formula x minus mu divided by sigma. For population proportions, z is equal to p-bar minus p divided by the square root of p times 1 minus p over little n, where p-bar is the sample proportion and p is the population proportion. For our example, we need to convert 0.6 and 0.7 to find the comparable z-scores. So 0.6 minus 0.65 divided by the square root of 0.65 times 0.35 divided by 200 is 0.6 minus 0.65 divided by 0.0337. Remember, we calculated that earlier, which is minus 1.48. Now we do the same thing for 0.7. We take 0.7 minus 0.6 divided by 0.0337 and we get positive 1.48. Let's mark this off on the distribution curve with minus 1.48 below the mean and 1.48 above the mean. Now looking up 1.48 in the z-table, we find 0.9306. And looking up negative 1.48, we get 0.0694. So subtracting 0.0694 from 0.9306, we get 0.8612. So we would expect in a sample of size 200 that 86.12% of the sample proportions will be within 0.05 or 5% of the true population proportion of 0.65. That is between 0.6 and 0.7. Now let's talk a little more about sampling. We discussed previously how to take a simple random sample by using a table of random numbers or generating random numbers using a computer program such as Excel. If every element in a population is assigned a random number, then every element has an equal chance of being selected. This type of sampling, simple random sampling, is a type of probability sample. There are several other variations of probability sampling methods that are used in practice depending on the situation. One variation of simple random sample is called a systematic sample. We use this to save time in assigning and assorting through large lists of random numbers. In a systematic sample, we use a random number to pick just the first element in the population and then systematically move through the population, picking elements at equal intervals until we have our desired sample size. So let's say we have a population of 1,000 elements and we want a sample size of 50. We would need to sample one element for every 1,000 divided by 50 elements, which is equal to an interval of 20. To put it another way, if we use an interval of 20 50 times, we will have a sample of 50 from the population of 1,000. The first element is picked randomly from the first 20 elements, so let's say we randomly pick the 17th element. Then, since the interval is 20, moving systematically through the population, the next element sampled would be the 37th item, then the 57th item, then the 77th item, and so on at intervals of 20 until we have a sample of n equal 50. This is called a systematic sample, and it is a type of probability sampling. Another commonly used probability sampling method is called stratified random sampling. In this case, the elements of the population are divided into homogeneous groups called strata, so that each element in the population belongs to one and only one stratum. To get these homogeneous strata, we might use a characteristic such as age, and then each stratum would contain respondents with similar ages. So for example, we might have one stratum containing young people, one stratum with younger middle-aged people, one with older people, and one with people close to retirement age. What is important is that each stratum contains similarly grouped items so that the populations within the strata are homogeneous, but between each group they are heterogeneous or different. This results in less variation within each group and allows for smaller sample sizes. Once the strata are grouped, then a simple random sample is taken from each stratum. Cluster sampling is another type of probability sampling method, but instead of dividing the population into homogeneous groupings called strata, the population is divided into heterogeneous groups called clusters, and then a simple random sample of the clusters is taken, and all elements in each sampled cluster are used in the sample. If many clusters can be obtained that are very similar, with each one being a miniature representation of the population, then only a few of these clusters need to be sampled to get a clear picture of the population. An example of this might be a large city that is broken down into city blocks as clusters, and then a few of these city blocks can be sampled as a representation of the population. Another grouping of sampling methods is called non-probability sampling methods. Here, the probability of an element being selected is unknown. The most typically used type of non-probability sampling method used is called a convenience sample. This type of sample is obtained by taking the most conveniently available items in a population. This may be done by going to a mall and sampling people as they walk by, or asking students to volunteer to fill out a survey. The problem with a convenience sample is that it could provide biased results, and the researcher must think about whether a probability sample would have produced different results, or is the convenience sample an adequate and fair representation of the population. Another type of non-probability sampling method is called a judgment sample, where experts or people with the most knowledge of a subject are selected for a sample. The premise in this type of sampling is that these experts understand and represent the opinion of many other people, and therefore a smaller sample can result in good information. This, as with any non-probability sampling method, must be used cautiously before using the results to come to conclusions or make decisions. It can be used more confidently in exploratory research, where the goal of the study is to gather information without drawing conclusions or making decisions. That concludes this tutorial on sampling and sampling distributions. We have only slightly touched on the topic of sampling in this tutorial. The methodology of sampling is a science in its own right and deserves much more than discussed in this video. In this video, only the basics of sampling methodology was discussed, with an emphasis on understanding the sampling distributions of X-bar and P-bar. I hope you enjoyed this tutorial, and I hope you learned something.